Earlier we have proved that the product of two connected spaces is connected. Similarly, we can show that product of any finite number of connected spaces is connected. Today we will discuss arbitrary product of connected spaces. In fact, we shall show that product of an arbitrary collection of connected spaces is connected. Recall that if xt and yv be two topological spaces, then for x in x, the space singleton x cross y is homeomorphic to space y. We have proved this result earlier. Similarly, we can show that for an arbitrary collection of topological spaces, x lambda t lambda, lambda belongs to an arbitrary index set capital lambda, the subspace Cartesian product of y lambda lambda belongs to capital lambda, where y lambda is equal to x lambda for lambda is equal to mu1, mu2 and so on up to mu n, and y lambda is equal to singleton x lambda for all lambdas other than mu1, mu2 and mu n of the product space is homeomorphic to the space x mu1 cross x mu2 up to x mu n. Now we shall prove the main theorem. The theorem states that let x lambda t lambda, lambda belongs to capital lambda, be an arbitrary collection of topological spaces, and let x is their Cartesian product. Let T be the product topology on space X. Then xt is connected if and only if x lambda t lambda is connected for every lambda in capital lambda. That is, to show that product space is connected if and only if each coordinate space is connected. Let us prove this theorem. Let xt be connected. That is, suppose product space is connected, then we have to prove that each coordinate space is connected. As for each lambda in capital lambda, the projection map pi lambda from x to x lambda is onto and continuous. We have proved this earlier, and we know that the continuous image of a connected space is connected, so each coordinate space is connected. Conversely, let each coordinate space be connected. Then we have to prove that the product space is connected. So now we consider a fixed point of product space X. Let A is equal to A lambda, lambda belongs to capital lambda, be a fixed point in X. And we know that any point of a topological space is contained in exactly one component of the space. So let C be a component of X containing point A. We shall show that all the points of X are contained in the component C. To show this, first we shall show that each point of X in the space X is an adherent point of a connected subset of C. That is, for each neighborhood n of X, there exists a connected subset A star of C such that X belongs to closure of A star. That is, any point of X is an adherent point of a connected set A star. So let x is equal to x lambda, lambda belongs to capital lambda, be an arbitrary point of X, and let n be a neighborhood of X. Let G is equal to Cartesian product of G lambda, lambda belongs to capital lambda, be a basic open set contained in n containing X. Because we know that for each point and for each neighborhood of that point there exists a basic open set. So here we are taking G as a basic open set, and we know that a basic open set in the product space only finite a number of coordinate spaces are restricted. So here G lambda is equal to X lambda for all lambda other than mu1, mu2 up to mu n. And that means G mu1, G mu2 up to G mu1 are the proper subspaces of x mu1, x mu2 up to x mu n. Now we find the required connected set. We know that the set A, where A is Cartesian product of y lambda, lambda belongs to capital lambda, where y lambda is equal to x lambda for lambda is equal to mu1, mu2 up to mu n, and y lambda is equal to singleton A lambda for lambda other than mu1, mu2 up to mu n is homeomorphic to x mu1 cross x mu2 up to x mu n. By hypothesis, each coordinate space is connected, and we know that the product of finite number of connected spaces is connected. So x mu1 cross x mu2 up to x mu n is connected, being homeomorphic to a connected space, that is this space x mu1 cross x mu2 up to mu x mu n. A is also connected. Clearly A contains the point A. Actually we have constructed A such that point A is contained in A. We note that G contains a point Z is equal to Z lambda. Lambda belongs to capital lambda, where Z lambda is equal to X lambda for lambda is equal to mu1, mu2 up to mu n, and Z lambda is equal to A lambda for all lambdas other than mu1, mu2 and so on up to mu n, which is also a point of A. So we find a point in G which is also a point in A. And since G is contained in N, so this point is also contained in N. So we can say that the neighborhood N of X contains a point of A, that is N intersection A is non-empty. So here we have considered a neighborhood of X, and we have shown that N contains a point of A. Now we consider all the neighborhoods of X. So let N of X be the collection of all neighborhoods of X, and here we are denoting it by NS, S belongs to S. So similarly, for each S belongs to S, a neighborhood NS of X, and for each basic open set GS contained in NS containing X, we can find a connected set AS such that A belongs to AS and NS intersection AS is non-empty. Recall that for the basic open set G, we have constructed a set A such that N intersection A is non-empty. So for neighborhood N of X and for basic open set GS contained in NS containing X, we find a connected set AS such that A belongs to AS and NS intersection AS is non-empty. As each AS contains the point A, so intersection of AS is non-empty. And so their union is a connected set, because we know that if intersection of connected sets is non-empty, then union of those connected sets is connected, and so union of AS, S belongs to S is connected. And since each AS contains A, so this union of AS also contains A. Let A star is equal to union of AS, S belongs to capital S, then clearly NS intersection A star is non-empty for every S belongs to S. Why? Because NS contains a point of AS, and here this A star is union of all A's. So NS contains a point of A star also, and so each neighborhood NS of X contains some point of A star. It follows that X is an adherent point of A star, that is X belongs to closure of A star. As A star and C are connected sets such that A belongs to C intersection A star, because earlier we have taken C a component containing point A, and we have shown that A belongs to connected set A star, so A belongs to C intersection A star. And since both are connected set and their intersection is non-empty, so their union, that is C union A star, is a connected set such that C is contained in C union A star. But as C is component, so we know that it is a maximal connected set. It cannot be properly contained in any larger connected set. So C must be equal to C union A star. And this implies that A star is contained in C. And this implies that closure of A star is contained in closure of C. As C is a component, so C star must be equal to C, and so we can say that closure of A star is contained in C. As we have shown that X belongs to closure of A star, and so from this we can say that X belongs to component C. As X is an arbitrary point of capital X, so we can say that every point of X is contained in C, and so we can say that capital X is contained in C. As C is a component, and so C is contained in X, and so we have the equality, that is C is equal to X. As C is connected, so X is connected. Thank you.